determine the correct amperage for the ranges on the feeder, it's essential to understand how to apply Table 220.55 in the National Electrical Code. This table provides demand factors for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances over 1 3/4 kilowatts rating. The key to correctly using Table 220.55 lies in selecting the appropriate column based on the number of appliances. In this scenario, we have 9-10 kilowatt ranges. The initial step is to correctly identify the applicable column in Table 220.55. Because we're dealing with multiple household cooking appliances, we'll look to column B, which applies to more than 2 appliances. Using column C is incorrect in this context. Column C applies if all the ranges are not identical. If there are some ranges with different kilowatt ratings, but here, all ranges are identical at 10 kilowatts, making column B appropriate. Now locate the row corresponding to the number of ranges, which is 9. Column B provides a demand factor of 54 kilowatts for 9 ranges. This means that instead of calculating the amperage based on the total connected load of 9 times 10 kilowatts equals 90 kilowatts, we can use the demand factor of 54 kilowatts, which accounts for the fact that not all ranges will be operating at their maximum capacity simultaneously. This is in accordance with the standard method. Once we have the demand load in kilowatts, we need to convert it to volt amperes. Since 1 kilowatt equals 1000 volt amperes, 54 kilowatts equals 54,000 volt amperes. This is the total volt ampere load for the ranges and the feeder. Next, we determine the amperage. We're dealing with a 240 volt 3-phase feeder. Therefore, we need to account for the 3-phase voltage when calculating the current. The formula for calculating amperage in a 3-phase system is amps equals volt amperes divided by the quantity of volts times the square root of 3. The square root of 3 is approximately 1.73. Plugging in the values, we get amps equals 54,000 volt amperes divided by the quantity 240 volts times 1.73. Therefore, amps equals 54,000 divided by 415.2, which results in approximately 129.5 amps. Rounding this value up to the nearest whole number, we get 130 amps. This is the minimum calculated feeder amperage for the 9-10 kilowatt ranges, taking into account the demand factor from Table 220.55, column B, and the 3-phase voltage of the feeder. In summary, firstly, correctly identify the applicable column in Table 220.55 based on the type and number of cooking appliances. In this case, column B is appropriate for 9 identical household ranges. Secondly, find the demand factor corresponding to the number of ranges in the selected column. For 9 ranges in column B, the demand factor is 54 kilowatts. Thirdly, convert the demand load from kilowatts to volt amperes by multiplying by 1000. This gives you 54,000 volt amperes. Fourthly, calculate the amperage using the formula for 3-phase systems. Amps equals volt amperes divided by the quantity volts times the square root of 3. In this case, amps equals 54,000 divided by the quantity 240 times 1.73, which results in approximately 129.5 amps. Fifthly, round the calculated amperage up to the nearest whole number. This gives you a minimum feeder amperage of 130 amps. When using Table 220.55, it's crucial to understand the specific conditions and requirements outlined in the National Electrical Code. Always refer to the latest edition of the NEC and consult with a qualified electrician or electrical engineer for guidance on specific applications and installations. Misapplication of demand factors can lead to undersized feeders, which can result in overheating, voltage drop, and potentially dangerous situations. It's also important to consider other factors that may affect the feeder sizing, such as conductor ampacity, overcurrent protection, and voltage drop limitations. These factors are addressed in other sections of the National Electrical Code and should be taken into account when designing and installing electrical systems. To further clarify the application of Table 220.55, let's consider a scenario where the ranges are not all identical. For example, suppose we have 5 10 kilowatt ranges and 4 8 kilowatt ranges. In this case, column C of table 220.55 would be applicable because the ranges are of unequal rating. To use column C, we first calculate the total connected load of all the ranges. This would be 5 times 10 kilowatts plus 4 times 8 kilowatts, which equals 50 kilowatts plus 32 kilowatts, or 82 kilowatts. According to the notes below table 220.55, when using column C, the maximum demand in column C is increased 5% for each kilowatt or major fraction thereof by which the rating of the largest range exceeds 12 kilowatts. In this case, none of the ranges exceed 12 kilowatts, so there's no need to increase the demand factor. From column C, the demand factor for 9 ranges of unequal rating is 41%. Therefore, the demand load would be 41% of 82 kilowatts, which equals 33.62 kilowatts. Converting this to volt amperes, we get 33,620 volt amperes. Now, we can calculate the amperage using the three-phase formula. ANS equals 33,620 divided by the quantity 240 times 1.73, which results in approximately 80.2 amps. Rounding this up, we get 81 amps. In this scenario, where the ranges are of unequal rating, the demand load and feeder amperage are significantly lower than in the previous scenario where all the ranges were identical. This illustrates the importance of correctly identifying the applicable column in table 220.55 based on the specific characteristics of the cooking appliances. It's also important to note that table 220.55 is just one part of the overall process of sizing electrical feeders. Other factors, such as conductor ampacity, overcurrent protection, and voltage drop, must also be considered to ensure a safe and reliable electrical system. Always consult with a qualified electrician or electrical engineer for guidance on specific applications and installations. In addition to table 220.55, there are other sections of the National Electrical Code that may be relevant to the sizing of feeders for cooking equipment. For example, section 220.14 covers the general requirements for calculating the load for household cooking appliances. This section states that the load for household cooking appliances rated over 1 3/4 kilowatt shall be calculated in accordance with table 220.55. However, there are some exceptions to this rule. For example, if the cooking appliances are used for commercial purposes, such as in a restaurant or cafeteria, the demand factors in table 220.55 may not be applicable. In such cases, it may be necessary to calculate the load based on the actual operating characteristics of the appliances. Another relevant section of the NEC is Article 422, which covers appliances. This article provides requirements for the installation and wiring of appliances, including cooking appliances. It's important to comply with these requirements to ensure that the appliances are installed safely and correctly. In addition to the NEC, there may be local codes and regulations that apply to the installation of electrical systems. It's important to check with the local authorities to determine if there are any additional requirements that must be met. When sizing feeders for cooking equipment, it's also important to consider the potential for future expansion. If there is a possibility that additional cooking appliances will be added in the future, it's a good idea to size the feeder to accommodate the additional load. This can help to avoid the need for costly upgrades in the future. Another important consideration is the type of conductors used for the feeder. The conductors must be sized to carry the calculated load without exceeding their ampacity rating. The ampacity rating of a conductor is the maximum amount of current that it can safely carry under specific conditions. The NEC provides tables that list the ampacity ratings of various types of conductors. When selecting conductors, it's important to consider the ambient temperature and the number of conductors in a raceway or cable. These factors can affect the ampacity rating of the conductors. Overcurrent protection is another critical aspect of feeder sizing. The feeder must be protected by an overcurrent device, such as a circuit breaker or fuse, that is sized to protect the conductors from overload and short circuits. The overcurrent device should be sized no larger than the opacity of the conductors. Voltage drop is also an important consideration. Voltage drop is the decrease in voltage that occurs along a conductor due to the resistance of the conductor. Excessive voltage drop can cause appliances to operate inefficiently or not at all. The NEC provides guidelines for limiting voltage drop in feeders. It's important to calculate the voltage drop in the feeder to ensure that it is within acceptable limits. In addition to these technical considerations, it's also important to consider the cost of the feeder. Larger conductors and overcurrent devices will be more expensive than smaller ones. However, it's important to balance cost with performance and safety. It's always better to err on the side of caution and size the feeder slightly larger than necessary to ensure that it can handle the load and provide adequate protection. In summary, sizing feeders for cooking equipment is a complex process that requires careful consideration of various factors, including the type and number of appliances, the applicable codes and regulations, the conductor ampacity, the overcurrent protection, and the voltage drop. It's important to consult with a qualified electrician or electrical engineer for guidance on specific applications and installations. Always refer to the latest edition of the National Electrical Code and any applicable local codes and regulations. Remember to always prioritize safety and ensure that the electrical system is installed correctly and in accordance with all applicable codes and regulations.